I think this is the strongest audience I've given a talk to, so it's pretty nervous. But anyways, thank you so much for coming to my talk. My talk is about ZKP security, but to be more detailed, we're going to try to gather some insights from it, and we're also going to try to get some insights on the Taxonomy of ZKP Vulnerabilities. So we're going to discuss about why certain bugs happen, and it will turn out that the main reason for why all these bugs happen is that the circuit, purely when we're thinking about the circuit side, the reason for all of these bugs are that when you're implementing a circuit, the language you're interacting with exposes a lot of cryptography to the surface level, and because that cryptography is quote-unquote new to the people who are just used to developing quote-unquote usual applications, so these new cryptography, the addition of this new cryptography leads to certain classes of bugs, and we'll discuss how each part of this new cryptography leads to a certain bug, and so on. So before we get into the major points, I want to go through the brief history of how we became to understand the bug classes. So as for me, this is more of a personal story rather than a history. But anyways, my understanding of this entire ZKP bug class stack is back when September 2022. This was when Zurich Park, very cool people by the way, Zurich Park's ZK security group kind of kicked off, and they tried to do a lot of different things. And one of the things they tried to do was Kyle at PSC, I believe, wrote the first draft of the now very popular ZK bug tracker repository on Zurich Park's GitHub repo. And as you can see here, I helped them review the thing, which was pretty cool. It was the very early days, 2 years ago. So the results from that initial draft of the ZK bug tracker was looking something like this. So you have some so here you have some good initial bug classes. So you have some classic stuff like under constraint circuits, overflows and underflows, bit lengths, and also some more cryptographic bugs in Broad 16. If you just forget to add a dummy constraint, it can get optimized out and you'll have malleability issues. So those bugs are there, and also some more cryptographic bugs like frozen hard and some weird things happening in the trusted setup. So overall, this is still raw, but the basic ideas of what types of bugs there are already developed. So that's pretty nice. And later when I studied a video in ZK Study Club by JP Alonso, there was this very nice slide from the talk. This is back in April 2022. So what this slide does is that it breaks down the entire ZKP development stack into layers. So you have a computation. You want to in ZKP you want to prove that you've done a computation correctly, right? So you have a computation, then you turn that computation into a circuit, and to turn that computation into a circuit, you fit it into a specific arithmetization. That could be RLCS or Plonkish or whatever. And then you do some cryptographic magic to make it into an unencrypted proof, and then you use that prover verifier system, and you shove it into into your application so that it integrates everything correctly. So because we can take layers, make the entire ZKP development stack into layers. What you can also do is that you can apply this kind of idea into vulnerability finding. So each of these layers have their own possible ways where a bug can happen. So some initial layering ideas emerge, and later June of last year, I gave a talk on Ethereum Soul. Basically, the idea was that this idea is also prominent in my talk right now, but the main idea is that the reason for why the circuit bugs happen is, the reason why circuit bugs happen is because, let's say you're working on Halo 2. The reason why when you're writing a Halo 2 circuit, the reason why these bugs happen usually is either that you made a mistake that you would made even if it was not ZK. So if it's application like specification bug, you would have made the same mistake whether or not you were like developing in a ZK circuit or a regular like smart contracts in Solidity or whatever. But more of the ZKP like specialized bugs happen because like you have to fit everything in a like targeted arithmetization. So let's say Plonkish. So because you have to like encode everything, every like part of your computation into Plonkish, there are specific like what's the word? Intricacies of Plonkish that make it difficult to like encode your computation into Plonkish correctly. And so my idea at the time was that you could take some properties of Plonkish, for example, any like ZKP friendly arithmetization. You can take Plonkish and inspect what properties this Plonkish arithmetization have, and from that you can actually just recover a potential vulnerability class. So for example, like very easy one is that Plonkish works over a prime field FP. And because we were working in FP, well, obviously like everything wraps up module P, so like all overflows and underflows happen because of that, and so on. So that was my like main idea of Iterative Soul talk. And then some big work has been come out recently on March, this year's March, and there was like this big paper by like 6 great people on our overall understanding of ZKP vulnerabilities. So they did a lot of things. They surveyed like current toolings and such. They surveyed lots of audit reports that are public. They went through all the bugs and they like classified like which bug, this bug, corresponds to this class and so on. And also another big thing that they did is this figure is taken from the paper. Another big thing that they did is similar to this slide. What they did was they broke down the stack into 4 layers. So there is the circuit layer where you encode your computation to circuit. There's the front end layer which handles the witness generation and like the whole compilation into like the constraints. And there's the back end layer which does the trusted setup if you need one. There's the whole proving, there's the whole verifying. That's all done in the backend layer. And finally, there's the integration layer where you take this system and put it into the application to make everything work out. So a very good layering done here. And while the work done by the SOK paper, I'll call it the SOK paper. The SOK paper is pretty great. I think there are some challenges that we still need to resolve. One is that we still need some better classification for the circuit layer issues. Because circuit layer audits are pretty dominant in the auditing scene right now. And we also need like more data set and work on the front end and back end. But this isn't really like the paper author's fault. Like the reason why there's like not a lot of data set in these 2 layers is that there hasn't been that many audits in these 2 layers. They are pretty rare. If you like go around and search for a like ZKP audit report, it's most likely going to be about circuits in the circuit layer. So like it is what it is. So but it's unfortunate, but it still is a challenge. But I think the main challenge that we still have to like solve is that we really need more insights from these surveys. And by insights, I mean like, so you collect all these like vulnerabilities and vulnerability types, and you kind of want to like get a conclusion from them that can like directly help the ZKP like overall security of the ZKP landscape. And I think like there has not been that much work to like extract some good insights from these like surveys. So that's the goal today. So like the ultimate goal on like why we work on this taxonomy or bug class or like reading all the reports is that we do this to like improve the ZKP security. And I think the biggest challenge right now in ZKP security is that we need more auditors. Obviously, in more mature places like smart contract security, we still need more senior auditors. Everyone complains that we need more senior auditors, and that's very true. But I think in ZKP security, even for junior level auditors, there's a shortage of it, and I think that's a problem. Like, you need junior auditors, and then those junior auditors become senior auditors by more experience and more studying. So I think we just need more people in general. And so to onboard more people, I think that these surveys about like bug classes should provide insights to like lower the barrier for ZKP security entry. ZKP already is a pretty has a high entry barrier regarding math and such. So I think ZKP security also has these barriers, and I believe that these surveys should aim to lower this barrier. So the game plan is that, as mentioned before, the big difference between the usual, let's just say that our target is smart contract security people who are very strong in their field, and we want to convince them to join ZKP security because there is some still like very similar context. So let's say that in that case, the new like factors that these people, these like strong auditors in the blockchain scene need to like get accustomed to is the quote-unquote cryptography exposed to the surface layer of what you're auditing. And you can just focus on this set, and you can focus on how to like explain this like cleanly and like without having such a big hurdle. You don't want to like make it sound too hard, harder than it already is. So what you can do is that you can just focus on this set and how to explain it to onboard strong Web3 security researchers to ZKP. So like on focusing on this set leads to following questions. When we're only like talking about the circuit layer and the integration layer, because front end and back end obviously requires very heavy math. It is like defined to be heavy math, so it's obviously like doing security work on those layers will need math. But when we're just talking about the circuit layer and the integration layer, these two questions are sufficient to onboard new security researchers. So point one for the circuit layer is that in circuit layer you're given a computation and you want to encode it into a circuit, right? So the main question is that, so if you're a ZKP developer, and you have a good sense of what kind of computation you want to like encode into a circuit, then the mistakes you make will be derived from the factors of Plonkish or whatever, or Gross16 or whatever, that makes like encoding the computation of a circuit hard, right? So you can ask this question, extract different kinds of factors of the automatization, and then recover some points that you may make a mistake, and then these ideas will be like directly connected to the vulnerabilities that one can find as an auditor. And for the integration layer, the main question would be like how one should like view these ZKP systems as black boxes, because integration layer is mostly about purely integration. You assume that the ZKP system itself is fine, but you integrate it wrong, and a bug happens. So for integration layer, the second question below would be sufficient to get a hang of it. And of course, like since we have as mentioned before, layering has been pretty important in our understanding of ZKP security. And the main reason why this is very important is that it allows to separate it and then attack it one at a time. So we should definitely utilize it. So because layering is possible, we don't have to worry about the witnesses being interpolated into a polynomial and committed into a polynomial commitment. We don't have to worry about it because those are in a separate layer. So we do need to utilize this as hard as we can to separate different kinds of audits that are out there and allocate each audits to people, auditors that are most fit for it. So main contribution here is that this line of thinking will give a very natural way to understand the bug classes that are out there. So you don't need to read all the audit reports to recover this line of bug classes. That's the one thing. And the second major thing is that I'll try to discuss about the additional mathematical prerequisites for auditors that are already strong on the smart contracts or other blockchain related environment. And finally, in this line of thinking will also give a relationship between the ZKP development metagame and what prerequisites the auditors will need. So basically, the reason why the third entry here, the fourth entry here is possible is that, for example, if you have, it's a spoiler, but anyways, if you have a very strong general purpose ZKVM, then you will be writing code instead of circuits, and because you're allowed to just write code, and then you'll be just able to compile it into a circuit. Now that developers are writing code, the quote-unquote cryptography exposed to the surface layer becomes 0. So the auditor who's also like reviewing the code itself doesn't really have to care because the cryptography exposed surface is also 0. So that makes ZKP security work a little bit differently than what it is right now. So that's the main point of the fourth line here. So let's talk about like what properties are there for like the plonkish that leads to like these kinds of bugs. So anyways, so of course like the circuit layer's point is to like turn a computation into circuit, and the constraint system should be security friendly. Okay, so like this is pretty much taken from the Ethereum Soul talk, so I'll be very brief. So basically, there is a line of bug class that's called assign not constraint. So what this bug is about is that you like compute some witness off circuit, and then you just assign it to the witness board, but you forgot to constrain it afterwards by some like implicit way. So for example, like if you are trying to do a division, like division and get a quotient and remainder, doing it directly in a circuit is very hard because the plonkish doesn't support it. So what you usually do is you just compute the quotient and the remainder off circuit, and then just constrain that A is BQ plus R, and R, the remainder R is less than the divisor B, and you just do it that way. So the reason why you have to go around like this is that you can't just straight up divide in the plonkish. So this is the reason why a limited set of constraints in plonkish kind of leads to this bug class called assign not constraint. So similarly, in a lot of circuits and a lot of chips, what happens is that they assume that a certain constraint has been already placed beforehand, even though that constraint is not very expensive when we're just talking in native land, because the constraints are expensive in ZKP land. So for example, like if I have an input that's like constrained to be between like 0 and 2 to the power of n, those checks are very easy in native our machine, but it's very hard to do it in ZKP because we have to you have to decompose it into bits and do all that. So this is why like many circuits assume that these kinds of checks has been done, but sometimes people forget that these assumptions exist and use the library in a very wrong way, and that leads to a very prominent bug class if you like really look at the circuits and audit them, called assumptions handling. This is also in the SOK paper. So in a way, you can say that constraints being very expensive, like even the most simplest constraints and most common constraints being very expensive, leads to this kind of issue. And so on for others. Like I already mentioned about like the usage of FP leading to overflows and underflows, and so on. So you can actually like do like this plonkish slash arithmetic is like some property to bug class kind of like pipeline, as shown in this slide right here. And some more additional bug class. These bug classes are in the SOK paper, but I do believe that, as I mentioned before, I do believe that some additional like work on bug classes can be done on top of the SOK paper, and it's these three. I'll be listing here. One class that they don't mention is that there are cryptography tricks used inside circuits in order to optimize it, and those tricks can be used incorrectly because obviously those are very non-trivial. So I can call this like set of bugs as incorrect cryptography tricks. And there's also like this one is in the Zelik's blog regarding ZKP security. Because the plonkish arithmetization has like a fixed witness board, like it has a fixed it has a fixed number of rows and columns, and like the constraints being applied on them are fixed because you have to like compile them and do what Plonk does, for example. Plonkish does, for example. This makes it very difficult for one to handle like variable length objects. Usually what one has to do is that you have to like assign a fixed maximum number of length of variables and have a separate variable for its actual length and handle it that way. And it becomes very like weird to handle, like easy to make mistakes. So there's that, and also like the PIP for Plonkish kind of makes it like the main idea of Plonkish kind of makes our constraints to be of two forms. One is for boundaries and one is for transitions. Like for example, in many like Halo 2 or Plonkish constraint systems, we either have a constraint that deals with a single row or two consecutive rows. And programming in this way does lead to several types of mistakes. One most prominent that I'll be discussing later. So there's like more pipelines in this fashion can be done if you just try to connect the usual programming patterns inside Plonkish and the bug classes that are apparent. And so speaking of like cryptography tricks, there's a lot different kinds of them. One is lookups. There's dynamic lookups, there's vector lookups, used with RLC, and there's also Fiat-Shamir. Fiat-Shamir can be used. Fiat-Shamir is also used in the backend when you're like doing the whole entire proving and verifying, but it can be also used within the circuit by, for example, if you're on Halo 2, there's this thing called phases. So you have like first phase things, and then after you write all the witnesses for the first phase, you can do a Fiat-Shamir there, and then that randomness can be used to generate witnesses for the second phase things, and so on. In order to like optimize your circuits. And there's also this relatively new technique called, not really new, but relatively new technique called offline memory checking, which can be used to simulate like memories in circuits. So that's pretty cool. And also in general, in a lot of different circuits, some mathy tricks are used. For example, if you're trying to implement an emulated field or multiplexers or whatever, some mathematical tricks will be used. And for variable length objects, as I mentioned before, they use a fixed maximum length array and a separate variable for its length. And there's like two ways this could go wrong. One is if you check like equivalence of two different things by using a random linear combination, one could pad this string with prefix or suffix, like depending on like how you accumulate stuff. You could use prefix or suffix zeros so that two different things accumulate to the same RLC, so that like they're considered the same even though they're different. And another very dangerous thing that could happen is that sometimes you will like allocate a fixed column, but it's not going to be fixed in practice because like the indexes of the entries of the fixed column is dependent on the variable length object. So sometimes handling variable length objects incorrect could lead to like fixed column not being fixed, like not being equal for like different instances. And this is one of the bugs we have found in like actual audits. This type of bug, yeah. So there's that. And another very common type of bug is this slide is reused. That's how common this is. But in a lot of constraints, you kind of accumulate something over multiple rows, and in many times they forget to handle either the first or the last row. Maybe sometimes they forget to like handle the final row's next row and something like that. A lot of weird stuff can happen. Like, for example, you can take the very first row and consider the previous offset of it, and things go very weird. So in general, like handling the first and last rows are very important, and this is something that's easy to miss because the way you write constraints, you have to like make two different kinds of constraints, and it's very easy to forget about one. So in usual cases, people forget to like handle the boundary constraints. So right now in this example, the constraint that's missing is that on the first row, the value in the accumulator has to be the same. With only like the constraint in the bottom, you could have accumulator being 668 and 687, and that's obviously not what we want. So there is that. And for the integration layer, as I mentioned before, for the integration layer, we could just handle everything by wondering about how we can view the ZKP system as a black box. So what we can do is that we can just black box it as like a user having a public input and a secret, and an approver compute the witness and the proof, and then the verifier checks the proof with the public input. And this will, because we're now in the integration layer, we can just assume that the circuit encodes the function you want to do correctly. So you can just say that the verifier's check will verify this computation F instead of the circuit C. So here we see that the main characters is the function F, the computation F, the public input xpub, the private value wpriv, and the proof itself pi. So by viewing each one of them, because these four are the main characters that are like exposed to you at the surface level, you can go through these objects one by one and try to like extract what kinds of bugs that could happen. So for example, say that you are wondering about like the function F. Here's because we are in the integration layer. F and the circuit are the same thing now. The main reason for vulnerabilities in this side is that the verifier will probably do the verification of F, the correct computation of F, and the verifier will do some stuff, some additional stuff, right? But these two combined might not be sufficient to constrain whatever application behavior you want to constrain. So this is more of a specification issue than anything else, and this is what smart contract security people will be very good at, like even without additional training. So that's good for them. So it's good that these people can like just join in and help out in these kinds of vulnerabilities. For xpub, this is the usual like constrain it to be less than p type of bug here. The reason why the bugs happen here is that the public inputs are supposed to connect the ZKP world and the verifier world. Like let's say it's on L1 or something. Then it's going to connect the ZKP world and the L1 world. But the native type for ZKP is the prime field FP. So unless you're on BDS, it's not going to be 256. But on the L1, it's probably going to be uint256, especially when you're just considering P is 256 bits. But the problem is that, of course, X and X plus P is different in uint256, but they are equal in FP, so there's like different types happening. And this type mismatch is what causes these bugs. So a solution, as we all know, is we force X on the L1 to be between 0 and P, so that we force the two types to be FP. Like instead of FP uint256, we force it to be FP. So this kind of deals. So if you handle this type mismatch correctly, then the xpub in the ZKP world and the xpub in the verifier world is exactly the same. So unless you're doing something weird that's probably going to be in this F land, everything's going to be fine. So you can just abstract everything away and just consider it safe. And for wpriv, the main task for wpriv is its secrecy, because that's.
A quick question on the previous slide. Are there rule checklists available to check these kind of things?
I'm actually not sure. But I do believe that this, especially for this, this is an area that tooling can definitely help, because it's so clear what you need to do. Yeah, so I think tooling can be definitely made. I'm not sure if it exists right now, but it can definitely be made. I hope somebody can do it.
I come from a very different background. I come from basic design work. There, the mistakes are very costly, but we have to basically go through the fabrication process again and get some knowledge. So in basic design work, the tools are really mature to catch these kind of issues.
Yeah. If there's a tooling, that would be great. Yeah, I do agree. To be honest, I'm not very knowledgeable on tooling in general regarding ZKP security, so I hope there is one. Yeah. And for wpriv, the leakage of this secret value is the most important part, but this is usually stemmed from a design issue, which is something that blockchain security people, infrastructure people are already great at. So there's that. And for finally the proof itself, the main idea regarding the proof, main attack idea regarding the proof is usually malleability slash front running. So the main idea here is that let's just say that in layer 1 there's this function that takes some I don't know, behavior t, public input xpub and proof pi, and what it does is that it verifies pi and then performs the action t. So what could happen is that if an honest person like submits ft xpub pi, the front runner can read the proof pi from a mempool and then just copy it and then just send ft prime, so different behavior, but with the same public input and proof pi, right? So this causes the layer 1 thingy to do t prime instead of t, which is very bad. And our usual defenses include just adding t to the public input to stop malleability issues. So this is the most classical ideas of using proofs to attack the system. And these conclude like the 4 main characters of the integration layer, and these are pretty much all the bugs. I think that all like the main ideas of all bugs found so far regarding like ZKP security. So now that we're done with like extracting all the like bug classes, we can like now talk about the prerequisites, the mathematical ones for ZKP security auditors. So we'll continue to focus on the circuit layer and the integration layer. So what you'll need is that obviously you'll need a very high level understanding of like a high level understanding of ZKP and its properties. You will have to understand the arithmetization you're working on very deeply. You will have to understand the field, obviously, because that's tied to the arithmetization very deeply. Well, but you won't have to understand how the PIOP and the PCP works. So you will have to deal with the like interpolation, computing the proofs, polynomial commitment, all that. You won't really need to like deal with them when you're just working on the circuit layer. And because, as I mentioned, there are some cryptographic tricks being used, and those are exposed to the surface level, like for example, like phases and such, you would need to have a good command of them. And if your constraint system makes use of these mathematical tricks, you would definitely have to have a good understanding of it. And also, as mentioned, there are some malleability attacks that are possible, so you would have to like know this as well. But the problem is that, of course, like these 4 things practically represent the set I mentioned before. The auditor needs to know these things because these 4 things are the cryptography that's exposed to you at the surface level, right? So, of course, since everything is exposed to the surface, the auditor has to like understand everything, right? But the interesting thing is that while these like cryptography that are at the surface level are hard and difficult to grasp like completely, they have relatively simple conclusions and quote-unquote APIs that one can just take it for granted, and it'll make the auditing experience more or less the same. So I'll be explaining that later. So these conclusions can be like just taken for granted and be used as a black box, and we can actually like do some additional layering inside the circuit developing experience to like make more black boxes available for the auditors or developers. So using these correctly, using these like techniques and black boxes correctly will help in reducing the workload regarding like mathematical prerequisites for the auditors. So by this, I'll like explain the main ideas. So for example, let's just talk about the malleability stuff, right? Obviously, like the idea and like the cryptographic idea behind the malleability attacks are like very non-trivial, but the interesting thing is that the most of the work is done already by cryptographers, and we can just use their results. For example, if you're working on KCG-based stuff like Plonk, they are proven to be simulation extractable. Also, they are proven to be non-malleable. This is done in the print paper here. This was also talked in ZK Summit 9, I believe. So if you're working on Plonk, you don't need to really worry about like malleability attacks in general. So like, of course, like the attacks in this is still possible because like the public inputs don't have the intention T. But figuring out that this is a vulnerability doesn't really require that much math. To be honest, it's like a design issue more than anything. So for Plonk, you don't really have to have additional like cryptographic understanding. And for Groth16, of course, it's known that this is malleable. Like in some polygons not being used, it can be malleable. But also the interesting thing is that usually these are handled by the backend layer by just adding dummy constraints there. So the usual circuit auditor don't really have to worry about these things too much. And of course, as mentioned before, the remaining attack ideas on proof pi is pretty like straightforward and doesn't require that much mathematical background. So there's that. And similarly, this is like the big idea of like how I view like circuits in general. So like on the bottom layer, we have like the proof system, the basic arithmetization and all that. And on the top, we have some cryptographic trickery like lookups, Fieschamir, and memory, like offline memory checking and so on. And sometimes, and oftentimes, there are an additional layer called libraries. Like we use libraries all the time in smart contracts, and it's similar for ZKP as well. For example, these libraries can handle uint, ECC hash, emulated fields, multiplexers, subarrays, data structures, byte operations, bit operations, all that. And the circuits can, of course, use the proof systems, like the API for, like handling variables and assigning constants and those stuff directly. They can also utilize lookups via Shamir memory to, make the circuits go faster. And they can also use these chips and libraries to make the developing easier, right? So, in a way, if you have like, in usual smart contract security, like if you use OpenZeppelin, if a project uses OpenZeppelin library, of course we do take a look at the OpenZeppelin libraries, like basic assumptions and how it works and such, stuff like that. But nobody like really takes a deep dive into OpenZeppelin library and like audits it completely. We usually assume that the basic fundamentals of OpenZeppelin code is safe. So similar to that, like for example, if there's like a fixed library that a lot of people have looked at it, and a circuit utilizes these circuits, that reduces. So for example, like in usual case, implementing uint 256 in Halo 2 or Plonky 2x or whatever is not non-trivial. But if there's a known library beforehand that implements uint 256, then a circuit writer can just use that library. And now a layer of like cryptographic madness has been like lifted off from our shoulders, and it makes everything much more easier. So it reduces the number of like exposed cryptographic tricks. So it makes both developing and auditing require less math in general. And also, let's talk about the like cryptographic tricks we mentioned, the Fieschamirs, lookups, and memory checking. For example, like in Fieschamir, like Fieschamir and how it works is pretty cryptographic. Like random oracle model and its related proofs are pretty hard to understand in cryptography. I still don't recall the Schnorr signatures, safety proof in my head. Like it's too hard. But their core ideas and core intuitions regarding security is like very intuitive. The main idea of Fieschamir and their security is that transcripts must have everything that's computable so far. And in that case, the hash is just considered as uniform random, and this is like exactly how random oracle model works anyway. So it's not like that. Like this kind of intuition-based thinking loses any information. Like this is how cryptographers think anyway. Like cryptographers do like more ungodly stuff with random oracle model, so it's fine. A lot of text here, but basically like the idea is that like for example a very common RLC application is to prove that the string C is a concatenation of A and B, and you use that, and to prove that you compute the RLC of these things A, B, and C, and one checks like this RLC based equation. But this RLC requires a randomness gamma, and the most important part regarding Fieschamir bugs is that how one should select gamma. And the intuition here is that if A and B are known, then the correct value of C is known in advance because C is the concatenation of A and B, right? So since A, B, C are all computable, what we do is that we just take the hash of these three things and shove it into gamma, and everything will be fine. And of course, if one forgets to include C, for example, and take gamma as a hash of A and B, the intuition is that one fixes the value of A and B, and that will fix the value of gamma because gamma is the hash of A and B, and then you fuzz with C to get a value that matches the RLC value, but C is not the concatenation of A and B, and you hope that it works, and intuitively, like it feels like it will work, and it actually does. Even though it doesn't really work that well, it's clear that it's a bug, so everybody will fix it. So of course, like launching a full attack regarding these like RLC related things might be more involved, might maybe like require more mathematics. So there's like the last challenge attack from OpenZeppelin has been discussed in this ZK summit. There's also the OG guys from Trail of Bits discussing the frozen heart vulnerability, lots of bugs there. And also back in Prague Crypto at DEF Connect, I think Sam Pretty discussed an attack on incorrect RLC by using some lattice techniques. So these does like require some level of cryptography, but I do believe that the most important part in auditing is finding the vulnerability rather than like making a full chain exploit. So finding the bug can be done with mostly intuition. So for example, for last challenge attack, like it's clear that the entire like transcript has not been shoved into the the entirety of the things that can be shoved into the transcript has not been shoved into the transcript, and that's why the bug happened. So at that point, it's already like known to be a bug, and the rest is like some exercise. So finding that bug, just finding the bug itself can be done purely by intuition, which is a good news for like auditors who don't really want to go into this like deep stuff. And also for like memory checking models, if you're doing a logarithmic derivative-based single array memory checking, you would probably like do something like this equation like above, but which looks difficult. But all it does is that over a fixed tuple of AVT, which is address value and timestamp, you are checking that the sum of input multiplicities are equal to the sum of output multiplicities over all those tuples. So of course, like here, the reason why like the equation above leads to the conclusion on the below is very non-trivial, and it's of course not very easy. But once you accept this fact, the core idea is that these like black boxes. So the line below here is the black box. These black boxes can help you reduce circuit auditing into less of a like paper reading session, like PhD level paper reading session, but it's more of a like, mathematical puzzle. It's a puzzle. It does require some math in a sense, but it's more of a puzzle than like hard math session. I think the puzzling aspect is more like bigger in ZKP security than people realize. So I wanted to get that out of the way. And while I did discuss some like good news for the people who didn't want to like go through the heavier ends of ZKP cryptography but still want to audit stuff. Here are some like news on the opposite side of it. So first of all, there is the hidden prerequisite that can be stemmed from the computation F. So like we kind of assume that indirectly assume that the computation F itself is pretty familiar to the auditors from the blockchain space, but in a lot of cases, this F itself can be quite mathematical. And obviously, in order to audit a ZKP implementation of F, you have to understand F very concretely. So there's like a hidden prerequisite there. So for example, if F is about elliptic curves, if F is about EDDSA verification, which is very complex, F is about cache functions, and in the extreme case, F is about snark verifiers. So you're doing a recursive snarks, or maybe you're doing folding. So there's the recursive part of the folding. In these cases, because your computation that you want to verify itself is already quite mathematical, you would have to know these things deeply to audit it, of course. So in general, having much better fundamentals regarding the stuff you want to audit will lead to more functions, more computations that you can actually audit. So you can actually audit more applications. So obviously, having better fundamentals will be good for you because you can audit more stuff. and of course there is the fact that prerequisites don't really equal to difficulty. Our discussion is really mostly about prerequisites, but difficulty is a very different thing. Even though like circuit auditing might not require that much math, it's still a very difficult task to audit implementations of very complex data structures. And also, like, of course, you need to understand Plonkish arithmetization, for example, to audit, because most circuits these days are based in Plonkish, so you need to understand this arithmetization, but it's pretty hard already. And also, in general, I do believe that the nerds type people are the most competent at such, tasks in like audits. So I think if one is a good auditor, even though I like tell you that this heavier cryptography side might not be actually needed, so you might need to focus more on the puzzle side of things. They would still like try to learn this deeper cryptographic things, because that's usually what good auditors do. They try to go into the deep ends. Like that's like all the qualities of good auditor. So like this talk is mostly about like not being scared of ZKP security too much, rather than like telling you that like I really don't want to be that person who's like, oh, you don't actually need this, you don't actually need that. I really don't want to be that person. Obviously, like knowing more is good for your skill, but this is more about not being scared of this space too much. So yeah, there's that. And also like, so the talk I did so far, it kind of leads to like this picture right here. So it's the same picture from before, but below the two arrows below are colored in red, and the two arrows on top is colored blue. So basically the blue arrows require less mathematics, less heavier mathematics. And the red arrows require some heavy math, some quote-unquote heavy math. So for example, like if you're just working over the chips and libraries that are already audited, then since you can use them directly as if you were just working on regular UN256 and so on, working over those would require would require less math, but more of a puzzle stuff. While building a UINT implementation or ECC implementation from scratch would require more mathematical tricks and therefore more mathematics to be able to competently audit it. So, but if you stare at this long enough, what you will get is like this, which is very scary for some people. Like for me, this scares me a little bit. So if you stare at this long enough, like the idea is that if one has good chips and good libraries and good front ends in general, that will make circuit auditing / circuit development very much like regular code writing, right? That's why these are colored in blue. So if this trend continues, what we will get is that we'll just get a ZKVM or like ZKDSL that doesn't really like expose lots of cryptography to the surface. And for example, like let's just say that there's or ZKDSL. Well, anyways. So the main idea of this picture that I like drew on iPad, anyways, is that one will write just code and shove it into a general purpose ZKVM, and that will like immediately turn everything into a good ZKP system. And if this happens, basically the state I was talking about before, the cryptography exposed to the surface, will be 0. And the meta will be something like write programs or code, not circuits. And this meta for developers would lead to audit code, not circuits meta for auditors. So it's like not saying that, oh, you don't actually need this or this for ZKP auditing. Turns into something like, oh, ZKP auditing and regular code auditing is now exactly the same, because we're now like writing code instead of circuits. So this is also a very good time to think about the strength of ZKVM. If you're like trying to learn ZKP security from the bottom up and you want to like make a bet on whether or not just studying the frontmost layer is sufficient, you would have to like make a bet on whether or not like a ZKVM might make your work completely like irrelevant, because now like, you're just reduced to just working on code that's shoved into ZKVM. But also at the same time, specialized circuits are important for optimization. But maybe but maybe like ZKVMs are strong enough to like make those specialized circuits irrelevant. Who knows? But at the same time, if there are specialized circuits, so for example, if I'm a person who knows like only the arithmetization and stuff like that, and I claim that ZKVMs might exist, but that does not make my knowledge irrelevant because specialized circuits will exist, and I'll be able to do circuit level front layer audits on those specialized circuits. That might not be true because specialized circuits usually will be like heavily optimized, and those heavily optimized circuits will not just simply use libraries, and it will try to like optimize more. So like it will use all tricks that are like on your hands. So auditing those specialized circuits would require lots of like deep fundamentals. So basically, you can't expect that this kind of like structure would exist in those specialized circuits. Specialized circuits would probably like use everything at once, so that like all colors are pretty much red in this picture. So it's kind of hard to like bet on it. So after the ZKVM starts to build up, the picture looks something like this. So here, the blue arrows are representing the stuff that doesn't require that much math. The red arrows represent something that requires a good understanding of cryptographic tricks and math tricks. So you need some mathematical stats to handle those stuff. And the green stuff is added here, and those represent a complete understanding of the entire ZKP stack. So something like this. So the bottommost layer is probably like the actual like Stark verifier or something like that. So those require very good understanding, like full paper level understanding of the Stark, and so on. So you can like divide the ZKP auditing into 3 layers, and each of these 3 layers will require different levels of mathematics. So you can like pick and choose. And overall, if you're considering about like if you think about the ZKVM meta, there will be less circuits to audit because everything will be written in like a lot of things will be written in code. So circuit layer audits won't be like as dominant as it is right now. Like right now, circuit layer audits consist of like 90% of audits right now. But if there's a ZKVM, many of those circuits will be just code. So less of them will exist. And that would lead to front and back end layers becoming a big target. While right now those didn't receive as much attention because there are less audits available. As time passes, these layer audits will receive more attention as their portion will increase. And also, if you're building a VM, the computation we discussed, the computation F we discussed is about building a VM. So obviously to audit a ZK VM, you need to know how VMs work. So there's also that. So overall, if you combine these together, it kind of like leads to the conclusion that the meta rewards heavy cryptography fans, heavy math fans, and heavy compiler fans, heavy VM fans. So the most nerd-snide people on the planet. So like it's a very like the duality of that. Yes. The duality of this talk is like you might not need to be nerd-snide, and B, but the meta will reward nerd-snide people. So take it away as you like. So which is kind of bullish for me because I recently this is a self-show, but I recently found like a weird like cryptographic mistake. A weird mistake in like cryptography paper. So I can actually like do the heavy cryptography stuff. So it's just kind of good. I don't know. So anyways, yeah. So anyways, the conclusion here is that by plug and playing this ZKP development metagame, so like whether or not you use like lots of libraries or you use like deep, heavy like specialized optimizations, or you use ZKVMs, depending on this like ZKP development metagame, you can conclude that currently I do believe that there are plenty of areas that one without super heavy knowledge of math and cryptography can definitely help regarding security. And definitely some black box reductions and layer separations can help build intuition and help onboard people very quickly. And yeah, and so on. But in the ZKP meta, I do believe that strong knowledge on the entire ZKP stack will be very much appreciated, and also knowledge on more complex structures such as VMs and compilers will be also very important and a very good skill to have to be a good auditor. So conclusions again. So we gave an insights on the taxonomy by like thinking about the set cryptography exposed to the surface. The mistakes come from this set. So starting from the cryptography itself, we can kind of think about like how this property can like mess up with the developers' minds and make them cause mistakes, and they can be like mapped into a bug class. And also by like thinking about this set cryptography exposed to the surface, we can derive the auditor's mathematical prerequisites, and by using black boxes on additional layers and so on, we can separate this mathematical stack into parts, and this can like help auditors get a good sense of what they need to study in order to like audit what. So it makes everything more transparent in a way. And also finally we showed how to like use the big picture, like the one with arrows and stuff, to view the ZKP security landscape based on how people will develop ZKP circuits, and we focused on ZKVMs as a big example. So I hope like this kind of like helps you understand like how ZKP security will change based on how ZKP technology advances. I think it's a very good thing to think about if you're like interested in security in general. So yeah, I hope you guys learned something from it, I guess. Thank you. And some questions? Any questions?
So right now, would you say that
just before you say it, we got like 5 minutes for a question, guys. Okay?
So looking at the situation right now, would you say that there is a profile of a circuit auditor, mostly dominated by the skills you need to audit a circuit, or is there rather a circum auditor, like language specific, like a Noir auditor, Cairo auditor? How would you think about it? Is like the concept the dominant thing, or the language expertise?
That's a very good question, but I think my answer might not be directly related to your question, so I'm sorry about that. But I do believe that one of the things that is also like bullish on people who are nerds type is that there are like right now, even for the circuits, I think every ZKP team is still developing their own thing. Like there's no universal like fundamental layer, so that you kind of have to have a mathematical fundamental to like get accustomed to like other languages very quick, because there's so many languages out there. So yeah, I think that's another reason why like mathematical fundamentals are very like appreciated in general, unless you're like a very fast learner in general. But yeah.